That wouldn't have been good. So we're looking at 53.
Mr. Street, do you remember last year when I fell in the back of the
And took out a desk too.
Yeah.
It was like pretty dramatic.
So loud.
And I thought that Garrett had tripped you as you went by. No.
Yeah, you left your backpack in the aisle.
Mm-mm.
Yes, you did.
So it says, say what's wrong with the statement. And the statement is a rational function. No, that's not it. It says, oh, give an example of. I'm looking in the wrong place. Give an example of a rational function with a horizontal asymptote of y equals 3. Does that sound right, Garrett? Am I in the wrong? 53?
Yeah.
Okay, so if you remember from back in our AP prep days, to have horizontal asymptote, you need the polynomial over a polynomial, and they have to have the same degree. And then we need the coefficient of the numerator to be 3 times that of the denominator. So you could do something like, say, 3x plus 1 over x minus 1. I mean, there's lots of possibilities, because as x goes to infinity, then the highest powers of x in the numerator and denominator are going to dominate. So the plus 1 compared to 3x, as x goes to 1,000, a million, a billion, it's insignificant. So this will act like 3x over x, which is 3. So we say the limit as x approaches infinity of this will be 3. And that means we're going to have a horizontal asymptote of y equals 3.
Okay.
And I mean, it's not unique. You can come up with lots of examples. But that's the strategy. Others?
Could you do 56 on homework 7?
Is that the same one then?
Yeah, same one.
Okay, so a function that has exactly 17 vertical asymptotes?
Yeah.
You're just trying to punish me, aren't you? So number 56, we want something with 17 vertical asymptotes. Okay, and you know that we get a vertical asymptote when we get something that will be 0 in the denominator that doesn't cancel with the numerator, right? Because if we had something, I'll do it on the side. So if you had something like x times x plus 2 over x times x minus 3, those would cancel. 0 would give us a 0 in the denominator, but that's not going to be a vertical asymptote. What's that going to be? A hole in the graph at x equals 0. So when they cancel, when they have the same thing that's going to be 0 in the numerator and denominator, that's going to be just a hole in the graph. Now here, we would have a vertical asymptote at x equals 3, because that's going to make the denominator 0, but won't cancel with the numerator. So all I need is 17 vertical asymptotes. So I got 1 over, there's 1, there's 2, whoops, there's 2, there's 3,
Okay.
and there's 17.
Wait, explain the whole again?
So this is going to give us a hole in the graph. So for example, if we were going to graph, I'm going to pick a little easier one. Let's do something like, say, x squared minus 1 over x minus 1. So you know that at x equals 1, this is 0 over 0, which is undefined. So there is no point on the graph there. But if you factor this, you can cancel those. So except that at 1, where it's undefined, everywhere else, it's going to look like the line y equals x plus 1. So there, when we know what y equals x plus 1 looks like, it's just going to be a line with slope 1, y-intercept 1. But at 1, it's going to be undefined.
Okay.
All right. What else? Okay, well, yeah, that's it, Miranda?
Yeah.
Okay, so we are going to talk about an introduction to continuity. So continuity is a pretty big deal in calculus. So our book only does it as one little section, and I don't think that does it justice. So this is going to be the last new topic in this chapter 1. And we're going to test on that, remember, a week from tomorrow. But,
I
and
have
you're,
a stat test on the thing.
well, who cares about stats anyway?
Okay.
So-
I'll talk, please.
So we can work something out. So I'm going to do another chapter just on continuity after we do this one. It'll be shorter, but we'll go into it in a little bit more detail than just what we're going to do here. So this truly is just an introduction to continuity, and we'll get down to the nitty-gritty much more in the next few days that come. Okay, so the idea is informally, and this serves us well. So we will talk about it formally, but informally, a function is continuous. And this idea, this conceptualization will serve us pretty well most of the time. A function is continuous if you can draw the graph without lifting your pencil from the paper. So this is not intended to be a formal mathematical definition. We will get that. And I may even just talk about it a little bit today. But first, I want to just kind of tease out, what do we mean, give some examples of what is a continuous function, and then talk about what are some examples of functions that are not continuous, or where are they not continuous and why. And you can see it from the picture that we draw, but I'm also going to give you some just examples of those functions as equations. And so these are going to kind of be nice examples to kind of keep in the back of your mind at least, because sometimes you need to draw on those, as at least in your own mind, if not specifically, about what is an example of a function that isn't continuous. We okay with this? Does that kind of make sense? So you can draw it without lifting your pencil. So a great example, we've done a lot with y equals x squared, and we know that y equals x squared is this parabola. It opens up, and it's got a vertex at 0, 0. So when you look at the graph, you can certainly graph that without lifting your pencil from the paper. So we would say, it would be correct to say that y equals x squared is a continuous function, period, end of story. You could say it is continuous over its entire domain. You could say that it has no discontinuities. All those mean the same thing. Okay? So let's look at some examples of functions that are not continuous everywhere. And in particular, notice where they are not continuous, which means where do they have discontinuities, and what about them makes them not continuous. So and I'm going to give you the equation as well as the graph. I think the graph will help make it make sense, and then I think knowing that there is an equation for it, you can kind of start to see what to look for. So we're trying to add this to our list of known functions. So can you, with your finger in the air, show me what the graph of y equals 1 over x looks like? Yeah, it's kind of like rubbing your stomach and patting your head, right? So it's going to be, you should be looking at something like this, okay? So it's got a horizontal asymptote y equals 0, vertical asymptote x equals 0. And like Tim was talking about before, it's got a vertical asymptote where the denominator is 0. That's going to make that vertical asymptote x equals 0. So the discontinuity, you can see that you cannot graph this thing. You start out here fine, but to go from here and skip over the asymptote, to skip over that vertical asymptote, makes it discontinuous. So we could say that, let me give it a name. We're going to call it f of x. So we could say f is discontinuous at x equals 0, because that's where the break is, where it's not connected any longer. You could also, but it would still be correct to say f is continuous, and this is, I think, sometimes what can get confusing. It is continuous on the interval from -infinity to 0, and also from 0 to positive infinity. So the only place that things go haywire is at x equals 0. But it is continuous on just those pieces there. So another example is something that is, say, y equals the absolute value of x over x. This probably isn't very, do you know what this looks like? Can anybody show me with their fingers what that looks like? Or I don't think we've talked about that in here. We will see this over and over again because it's a nice example of what's going to happen here. So the idea is when x is 0, this thing isn't going to work. 0 over 0 is undefined. So there's going to be no point on the graph at 0. Now, no matter what positive number you plug in, say 1, the absolute value of 1 is 1, and that's 1 over 1. Absolute value of 5 is 5 over 5 is still 1. Absolute value of 10 is 10 over 10 is 1. So any positive number you get there, because the absolute value just leaves a positive number as it is, you get the same thing over itself. It's always 1. So the graph is going to be undefined at 0. So open circle, but everywhere to the right, it's going to be just 1. So it's going to look like that horizontal line. Now, when you plug in a negative number, say you plug in negative 2, well, the absolute value of negative 2 is positive 2, divided by negative 2 is going to be negative 1. And negative 20 in absolute value is positive 20, divided by the negative 20 is also negative 1. So no matter what negative number you plug in, you're always going to get the same thing positive over the thing negative. And so it's always going to be negative 1. And so you get this, this thing that just looks like two pieces, and it's totally undefined at x equals 0. So this too has a discontinuity at x equals 0. Because that's where, if you're drawing it, you're going from left to right, you draw it, it's all fine. Well, then you got to lift your pencil from the paper to get up here, and then you're okay again from that point on. So we say that, and I'll call this g of x. So g is discontinuous, or has a discontinuity, either way, at x equals 0 once again. Okay? So discontinuous may be a little bit different kind of discontinuity than we saw for 1 over x. And let's take a look at, say, y is equal to, and we sort of saw one like this, the one that Garrett asked about a minute ago, sort of like this anyway. So if we have something like y equals x minus 1 over x times x minus 1. So we can see that we're going to have this value of x that's going to be 0 in the denominator, like the one Tim was asking about. So this, because there's nothing to cancel with it, is what's going to happen at x equals 0?
Vertical asymptote?
It's going to be a vertical asymptote, right? It's one of our 17, no, this is only going to have, not even going to have 2 vertical asymptotes. It's going to be a vertical asymptote. But here is what Garrett was talking about, because 1 will make the denominator 0, but at the same time it's going to make the numerator 0. And so we can think of canceling those. So this will act like 1 over x everywhere except at x equals 1. Because here, at x equals 1, it makes perfect sense. It's just going to be 1. But over here, this is not defined at 1. So how's that going to show up on the graph? That's going to be a hole in the graph. So what we're getting here now is our 1 over x looks like that thing. This is like rubbing your stomach and patting your head. You get that thing up in quadrant 1 and quadrant 3. So you got that vertical asymptote at x equals 0. But in addition to that, at x equals 1, we're going to get a hole in the graph. So now here is an example of a function that has 2 discontinuities, right? So, and I'm going to use the word discontinuity so I can hold on to my paper anyway. So we are going to, just so you see that word used. So I'm going to call this h of x. So we will say h has discontinuities at x equals 0 and also at x equals 1. There are different kinds of discontinuities. We'll talk more about this in the days that come because we're going to give names to them. But you can see they don't behave quite the same way. You know, one you got a vertical asymptote, the other one you just got this hole in the graph. And so we'll give those names down the road, but that will come a little bit later. Does that make sense? And you can tell it passes that kind of conversational definition. You know, if you're drawing the graph and you're coming along here, you got to lift your pencil from the paper to get over the vertical asymptote, but you're going to have to lift your pencil from the paper to hop over that hole in the graph as well. So two discontinuities for that function. Okay, and let's talk about, I'm going to give you, say f of x, I'm going to give you a little piecewise function here. So the first one we're going to look at like the one we used in Garrett's example earlier. So this is going to be x squared minus 1 over x minus 1. We're going to define it to be this way everywhere except at 1, because we know we got that issue going on at 1. So I'm going to redefine that at 1 to be something different. I'm going to say it's 4. Does that make sense what we're doing here? Okay, so if we graph this thing, now looking at the x squared minus 1 over x minus 1, we know that at 1 something goofy is going to happen because you're getting 0 over 0, right? 1 squared is 1, minus 1 is 0, 1 minus 1, the denominator is 0. But if we factor that, then we kind of get to the heart of the matter here. Really, the way this is goofing up is not that that's going to be a vertical asymptote, but in fact, it's just going to be a hole in the graph. So this is going to look like the straight line y equals x plus 1 everywhere except at 1. And we're not going to use this to define it anyway. So we start out with, you know, we're going to say here is our line, something like that. But at 1, we're going to have this hole in the graph. You with me? That's just this piece right here. So if that was the whole graph, if that was the whole function, we'd be done. It just has a hole in the graph. But now we're saying, wait, we're going to define it at that hole. So even though it wasn't defined in this piece, we're going to say when x equals 1, it's going to be 4. Well, that's not going to fill in the hole, right? We have 1, 2, 3. Get that out of the way. 1, 2, 3, 4. We're saying it's going to be defined to be that. What a strange function indeed, right? So now, we knew we had an issue at 1. Did we fix the problem in terms of it becoming a continuous function? No. So, you know, as you come along in here, you're still going to have to lift your pencil from the paper to put the dot in there, and then come back down here and continue. So this still has a discontinuity at x equals 1. So there is still a discontinuity at x equals 1. Just a little different kind of discontinuity than we've seen before. Okay, so we've seen these kind of things like, you know, a hole in the graph, a vertical asymptote, a hole in the graph that is defined somewhere but doesn't fill in the hole. And we'll get actually another one before we're finished, but I don't think we'll go into that just yet today because we're still just introducing this idea. Okay, so that's kind of the heart of what we're getting at here about discontinuities. Now, some nice things to know, especially, you know, when you're deep into AP calculus, maybe you're in the middle of a test. And sometimes it's nice just to know some things, to know you have a source of examples of continuous functions. And we'll talk about other characteristics that are nice that'll come up in the future as well. So I'm just going to call these nice facts. So these are things that you can know, I mean you can know, and you can even claim that this is true without having to justify it or prove it or anything like that on my test or on an AP test. So one thing is that all polynomials are continuous everywhere. Kind of nice to know. And we will see at the end of the day here even, you know, some theorems are going to have part of their hypothesis, or, you know, things, the conditions you have to satisfy to make the conclusion will involve, it has to be a continuous function. So it's nice to be able to say, oh, I know this function is continuous because it's a polynomial. You're good to go. Okay? So also exponentials are continuous everywhere, right? Growth functions, decay functions, you can draw all of them without lifting your pencil from the paper. So they're going to be continuous everywhere. Radical functions, think like y equals square root of x, y equals cube root of x. Radical functions are continuous, we will say, where they are defined. So something like y equals square root of x, we know that's going to be this half of a sideways parabola. So it is going to be continuous everywhere it's defined. It's not defined for negatives, but it is going to be continuous for x greater than or equal to 0. Okay? Cube roots has no problems. You know, the cube root of x does this kind of swirling thing in there. And so it's going to be continuous for all real numbers. So the even index radicals, square root, fourth root, sixth root, they're going to have issues with negatives. They're not going to be defined for negatives. But they'll still be defined wherever it's positive, wherever it's greater than or equal to 0. And then the odd root functions are continuous everywhere. Rational functions, and we see they can have some issues, right? So rational functions are going to have problems when you have a vertical asymptote, and they're also going to have problems when you have a hole in the graph. But everywhere else, so we'll say, like we did with radicals, rational functions are continuous where they are defined. Where they are defined. So as long as you don't have a 0 in the denominator of a rational function, you're good to go. So that's nice to know, because then you know where to zero in on. Where does this thing have discontinuities? Just look at the denominator. Where's the denominator going to be equal to 0? Now, trig functions get a little bit messy, right? So what are some trig functions that are continuous everywhere? Sine and cosine, right? Because they do the wave thing. And you can draw that without lifting your pencil from the paper. Now, all the other 4 are going to have issues, right? Because they all have vertical asymptotes. So tangent and cotangent and secant and cosecant are going to have discontinuities everywhere they have a vertical asymptote. Okay. Also nice to know. So I'll just put, still in nice facts. Adding, subtracting, multiplying. Notice I'm not going to say dividing. Continuous functions. Gives a continuous function. So you can do all kinds of crazy arithmetic with functions, and if each of the pieces is continuous, then however you want to combine them, is still going to be continuous. Why can I not say dividing?
Because if there's a 0 in the
Yeah, because now if the denominator is a 0, then it's not going to be continuous there. Okay, what's maybe surprising? Composition. So if you do f of g of x, and composition of continuous functions is continuous. So for example, if we say f of x is equal to e to the sine x, what in the world does that look like? I don't know. But we know that e to the x is continuous. That's just an exponential growth function. We know sine of x is continuous. That's just that wave. Composition, f of g of x, is going to be continuous too. So whatever crazy thing this looks like is still going to be continuous. Okay. All right, different kinds of problems. So let's look at piecewise functions. It's like a recurring nightmare, isn't it? It's a bad dream. It keeps coming back. And we're done with those. So I'm going to ask you to find K. So that f of x is continuous for all real numbers. So I'll just write for double bar r. So I'm going to give you a piecewise function. There's going to be a k that appears in there. What must k be so this thing is continuous everywhere? So we'll say f of x is going to be, and we'll say kx for x less than 2. And it's going to be 3x squared for x greater than or equal to. So if we think about it now, because we want to make sure we just see what the real issue is. The issue is going to be where these try to come together. You know, everywhere to the left of 2, a number times x is going to be just a polynomial. And we know that polynomials are continuous everywhere. So this piece of it, where it's defined, is not a problem. And 3x squared is also a polynomial. So it doesn't have any issues where it's defined. So the only issue that we have to consider here is where do these two pieces, do they miss each other and make it discontinuous, or do they connect and make it continuous? You know what I'm saying? So what we want to do is make the left-hand piece equal to the right-hand piece. Does that make sense? So the left-hand piece is going to be, so as we come in from the left, this thing's getting closer and closer to, we plug 2 in for x, and we get 2k. That makes sense? Miranda? Doesn't look like it made sense. As we come in from the right side, now we're kind of backing our way into 2, because this is good for everything greater than or equal to 2. As you come in here to this parabola towards 2, it's going to be 2 squared is 4 times 3 is 12. So that is going to be 12. So for these two to connect, then we need for the 2k to equal 12. Let me draw a breath. I don't feel like I'm, I think we have a discontinuity here in what we're understanding. So this is going to look like some straight line, and it's got slope k. So I don't know what that line is. So here's 2. So this thing is going to be some kind of line. Well, I'll come back to that. This is going to be a parabola 3x squared. Well, we know that 3x squared is going to be a really steep parabola, right? But at 2, this thing is going to be 12. Well, that happens to be 12 right there. And so this parabola is going to, this is the part of the parabola that we are including, because we only want the parabola for the values of x that are 2 and bigger. So we have a parabola, but we chop it off. The dotted part isn't going to be part of the graph. So I'm going to take it out of the picture. Now, this is going to be a straight line. It's going to go through the origin. Its y-intercept is 0. So we have lots of choices of straight lines that go through the origin. Now, we got to pick the k so that, you know, if I pick the wrong k and this thing does that, you know, we're going to have a discontinuity there because they're not going to be the same thing at 2. We have to pick k so that it ends up connecting with that end of the parabola, because then it'll be continuous. Right, I'll be able to draw it without lifting my pencil from the paper. We'll have the straight line part, and that open circle there is exactly filled in with the solid dot from there. And I can continue up on that parabola, and there's no break in the graph. So for that to happen, the end of this graph, which is going to happen at x equals 2, which is going to give us 2k, we don't know what the k is yet, has to match the end of this point of the parabola when x is 2, which makes that 12. So that means the correct choice for k is going to be 6. Does that make sense? Okay. You say that now. Let's see if you can do one. And I think it's time for you to come to the board to do this one. So let's say g of x. Remember, we want this to be continuous for all real numbers. And we're going to say it's k cosine of x for x less than or equal to pi. And we're going to say 12 minus x for x greater than pi. So we have to find k. So g of x is continuous. I'm just going to say continuous. Period. End of story.
No, get on the other board.
Well, it sure would be nice to know what the cosine of pi is.
-1.
Oh, I had a kid. Very good. You got that chart almost mastered. Wait a minute. See if anybody needs help. I think we're fine. So these have to connect. These have to be equal to the same thing at that boundary value of x equals pi. Bridger, can you jump in? You got it, Bridger. Can you help?
Okay.
No, you just keep it as x. Or no, actually, you put in, so you put in pi here, so it would be pi there as well. Yeah. And then you just divide them.
Oh.
I just wrote it as negative 12 plus. Negative 12 plus.
X plus 2.
Oh. Yeah, we agree. Negative 12 plus pi or pi minus 12. We're in agreement. We're in agreement.
Yeah, that should be minus.
We're doing another one.
No, I gotta get in the intermediate values down here. I wasn't counting on it taking you guys that long to do that problem.
I,
Oh, that's okay.
Yeah.
We'll do more down the road. It's a hard idea.
That's wicked.
So the intermediate value theorem is one of our first big named theorems. So, a theorem that has a name usually is pretty important, and this is one of the foundational ones. And this is a theorem about continuity. So it says if f is a continuous, if f is a continuous function, so I'm going to underline this because this is important. Continuous function on a closed interval. This is the other key piece to this theorem, is that it's going to be on a closed interval. And I'll show you that by putting the A and B in brackets. That means we include the A and we include the B. And K is any number between f of A and f of B. And I don't know whether f of A is bigger than f of B or not, or even if they're equal to each other, that doesn't matter. But I'm going to say then there is at least one number, and I'm going to emphasize that it's an x value, x equals c, in that interval from A to B, such that f of c is equal to k. So I'm going to try to give you a visual of this. I think it really makes sense when you see the picture. It can be a little tricky sometimes in understanding quite how you're going to apply it when it comes up in sometimes surprising places. So I'm going to imagine, here's an xy axis, and I'm going to imagine this is our function f of x, and f is continuous. And I'm going to say, here is A and here is B. And so here on my scheme is f of A, and here on my scheme is f of B. So the A and B are x values, the f of A and f of B are y values. So the idea is this is a continuous function. So if you pick any number k in between f of A and f of B, so I'm going to just randomly say right here is k. Then the claim is, what the intermediate value theorem says, is that the function must equal k for some number in between A and B. That it can't somehow, as you come along this function, skip over and miss k because it's continuous. It can't be a hole in the graph or an asymptote or whatever. Okay. You may have to just, there's some examples if you look at the end of the supplemental video there that might help, because this is going to come up, I think, on some of the homework problems. Okay. So that's the idea behind it, but how you use it, you may need an example.
8 and 9, Mr. Street, or just 8?
Just 8.
From Tuesday, just 8? Or 8 and 9?
From Tuesday?
Like the next Tuesday, we have 8.
Oh, 8 and 9, 8 and 9 both, yeah. Today is 8, tomorrow's going to be 9. Give me a minute, guys, so I can
Is it both? Yes.
sanitize.